Well, welcome to my warm and comfy editing suite. I've just completed the edit of my adventures in beam alignment land. Now, as a Thinklaser customer, what I'm just about to show you in the following video is not something that you need to do. The machine that you have bought is a very good machine. I know, because I've had a go at pulling it to pieces. I love the machine. But if I see something that isn't quite to my liking, I'm not in the least bit worried about pulling it to pieces and doing something about it. Now, I came across a small problem with beam alignment, which piqued my interest. The system of beam alignment on this machine is no different than that of thousands of other machines that come out of China. I happen to have a different machine with a different beam alignment system that I've been used to. So I found myself in a certain amount of deep water when I started fiddling with the beam alignment system on this machine. Now, the beam alignment system is not something that you will have to fiddle with. As an everyday user, if there's a problem, you will call in your service tech. I have a responsibility to you as a Thinklaser customer to make sure that you don't invalidate the warranty on this machine. What you see me do is not something that you necessarily need to do, want to do, or have to do. I'm afraid I'm an old school engineer, and warranties don't mean much to me. If I see a problem and I see a solution, I'll go about fixing it. Sometimes it gets me into trouble. Sometimes it leads me into new and green pastures. Now, what you're going to see today is a completely different approach to aligning and setting up the machine. The flexible standard kit that mounts the mirrors on these machines is a piece of kit that's used on all sorts of machine design. And as such, it has to be flexible. Now, that flexibility comes at a cost, and that's complexity of setup. Now, complexity of setup is not something that you will ever encounter because the mirrors are already factory preset. The most that you will have to do is probably just tweak the mirrors a little bit. But even then, I would suggest you probably don't, because there is no reason why the beam will go out of alignment unless you start thrashing the machine around. So you're going to join me in a session where I will explain what beam alignment's all about. Now, it's for your interest rather than for your doing. What it has done for me has made me realise that I think there's an even better way. That may be another adventure that you watch me undertake, or maybe it's something I should do behind closed doors, and you'll never know. It really depends on how Thinklaser view my re-engineering approach. So, sit back, relax, and enjoy, but don't do. Thanks very much. Let's get on with the video. Well, welcome to another Lightblade Learning Lab. I think you get the impression that this might be quite a relaxed session. I think you've got that wrong. It's going to start off in a very casual way, and it's all about beam alignment today. Now, beam alignment is actually a very simple subject, but it's a bit like entering a jungle without a map. You can very quickly get lost and not understand which way to turn. You need a compass, you need a map, and you could find your way through the jungle. What I'm going to do to start with is give you an outline, basically provide you with the map before we enter into this jungle. I'm not going to touch this machine myself again, because I've already, I wouldn't say burnt my fingers, but I learnt the hard way that this machine is not the same as my other Chinese machine over there, and that it requires a completely different strategy to set this one up.
Although I shall be focusing on this machine, anybody with a red sail clone will have similar problems because this is the style of machine that you will have. But anybody with the China Blue machine, like I have over there, well, I've already got well documented procedures for calibrating and setting the beam on that. But these procedures, the basic principles, this roadmap, will help you as well to understand how you should go about and why you go about things in a certain way, in a certain order. I just want to lay down a few ground rules before we start. This piece here, all round the outside, is what I would class as, on this drawing I've got here, it's called the Lightblade floor, and that is this flat surface here upon which everything is mounted. Then we've got the top surface of the gantry, which is this piece here. Now on this top surface we've got a bearing rail, and the head runs backwards and forwards on this bearing rail. And then we've got the Y bearing rails down the side here. Now the other key issue here is that this bearing rail is 90 degrees to these two Y bearing rails. Well, we're going to start off with a plan view of the machine. This is typical of any of these small lasers. We've got a laser tube, we've got our two 45-degree bending mirrors, got another 45-degree mirror to bend the beam down towards the head. And the other key thing here, whenever we bend the corner, we've got to finish up with the beam running parallel to the X or the Y bearing rail. That's an absolute fact. We cannot deviate from that. What's the problem? Well, the problem is, on this machine, we've got all sorts of degrees of adjustment and non-adjustment. For example, the head mirror itself is totally non-adjustable. It is what it is. It's fixed, and all it does, it moves backwards and forwards along this X-axis. Its angle can be adjusted very slightly, but it can't be adjusted that way, and it can't be adjusted in and out. We've got one mirror which is absolutely fixed in space. We've got this second mirror here, which is at the end of the beam. You can move it in X, you can move it in Y, you can rotate it a little bit, and you've certainly got adjustment on the mirror to just tweak the mirror. In addition to that, there's a further plane of adjustment which is up and down, which I haven't shown on that picture. And then we've got mirror number 1, which is the one that turns the laser as it comes out of the tube. Now that's only got basically 2 degrees of freedom on it. It can move this way across the plane of the beam. It's got a lot of twist adjustment on it, and it's also got some minor adjustment on it for just tweaking the mirror. The laser itself has got horrendous amounts of adjustment on it. You can swing it around, you can lift it up and down, you can twist it from end to end, you can twist it from side to side. You can basically swing the whole of that beam around in space like that. This is what we've got to finish up with, but how do we get there? That's the problem. Ideally, we'd like to finish up with this beam here running parallel to that bearing rail there. Is that absolutely essential? And as I tip the tube round by 5 degrees, you can see what happens. It misses the mirror. It's got to hit the central point of the mirror, otherwise it won't reflect. Okay, let's look at the next picture. We've corrected that problem now. We've moved the mirror in that direction there, and we've caught the beam on the centre of the mirror. But because the laser is tipped over at 5 degrees, and this is 45 degrees, we get a reflection off of that surface, which is there. You could say that we just move this mirror over this way and catch the beam. Well, and then we can steer it back towards this one. That is true. We could, if there was enough adjustment on there. But the problem is, we've broken golden rule number 1. We are no longer parallel to the bearing rail. So we can't do that. What we've got to do is adjust this mirror here. Let's see what happens when we adjust this mirror. Fine, look, we can put 2.5 degrees of rotation on this mirror, and we can make that beam run parallel here again. Brilliant. So we've got a degree of freedom here, and we have got some ability to fix the problem that's caused by misaligning a plan view of the laser tube. And we're back on plan again. So now this is running parallel. What can we do here? Sorry, I need my biscuit to come into play now. This just makes a great mirror, doesn't it? Until I eat it. We've already agreed that we can't move the mirror out of position, because if we do, the beam will be non-parallel to the rail. So that technically means there's only one position in, if you like, the x-axis direction for this mirror to be sitting. And that is absolutely in line with this mirror, so that it can pick up a parallel beam on its centre that's parallel to the bearing rail. We already said this mirror has got 0 degrees of freedom on it. We need a beam to hit the centre of that mirror, and it's got to run parallel to this bearing rail. Therefore, we cannot have, although that was moving this mirror this way would satisfy the parallelism in this plane, if it bounced off the mirror here, it would not be parallel in this plane. So by default, there is literally only one position for that mirror to be in. So you cannot mess around with these mirrors very much, and I'm very surprised that this mirror on this machine has got so many degrees of freedom. It doesn't need them, and it doesn't need them because the head is fixed. Okay, so this is the fixed head, and underneath this adjustable plate at the top here, we've got a gap. This head here and this piece are completely solid and fixed. They're fixed to the bearing and the bearing rail underneath. So there's 0 adjustment on there except for a small amount of swing on this plate, just to guide the beam. Okay, so you've seen what it looks like in reality. Here's what it looks like in detail. Now, I've done a fairly careful drawing and analysis of this machine. I've looked at it in great detail, and I've done all sorts of measurements on it, and I've done a good detailed analysis of the actual head assembly itself and what's inside here. The red is obviously the path, the ideal path of the laser beam. Now, when I say the ideal path of the laser beam, I'm going to explain that in a little bit more detail in a few seconds. What I want you to do is look at this drawing to start with. Now here is the mirror. So although it's a 25mm mirror, it's set inside a recess, and the exposed part of the mirror is only 23.1mm diameter. Well, I say 23.1mm diameter. If you were a laser beam coming at this, here's what you would see. You've got a hole in the front which is there, and I'll just put those 2 dots there to show you how they tally up. And that's the first thing I've got to see. I will see the entry to the head, but then hiding behind that I've got a mirror, and because the mirror is slanted back at 45 degrees, it's no longer 23.1 diameter. In fact, it becomes an ellipse. But of course, I can't, if I was the laser beam, I can't see the full mirror. So that's what the laser beam will actually see by way of a mirror. It's a very strange shape. And I've drawn this laser beam at 10mm diameter. Now, most people are going to say, well, the beam is only 4 or 5mm diameter. Well, I think we demonstrated the last time we looked at mirrors that that beam is something other than what most people think. Its influence, its power, its heat extends way out beyond maybe the point where it can do any damage, but that heat is still part of the power output of the beam itself. So we're going to investigate that a little bit further later on, but for the moment just assume that we've got a 10mm beam here. Let's be a little bit cautious, and you can see that we really don't have much room for error on either side to get our beam onto the center point of that mirror. Now, if we aim at the center point of the mirror, which is this point just here, and look, there's the center line of the mirror through here, and there's the mirror face just there, and we're aiming specifically for that point. The bad news is the design of this head is such that the center point of the beam does not run down the center point of the bore. This is one of the lens tubes that goes into the bottom of the machine. What we've got down the inside there is a 17mm bore. And what we're hoping to do is to aim that, we're trying to aim this beam at the lens which is in the bottom there. We really want to be on the center line or the axis of the actual lens itself. But at the moment, we're not. And we cannot be. Even if I remove this 1mm gap here, we shall still be slightly off center. So there's a fundamental design issue with this head. The other fundamental design issue with this head is exactly the same issue that I found with my China Blue machine. And that is that if we take a look here, you'll see that the center line of the true mirror center point is not the same as the port entry, i.e. the hole in the front here does not represent the true center line of the mirror. So I think that my little targets that I made are probably inaccurate and need remaking. A mistake I made. I didn't check the position of the mirror. It looked nearly right, so I designed my target to sit on the front there and assumed that the design was right. But now that I look at it in detail, I think you can clearly see, look, we're 1.3mm high. So there's several sorts of design issues with this head. Small details, but annoyingly important. Especially when we've only got a very small amount of error here. I mean, that's what 1.3mm looks like. Hey, that's nearly what we've got here, look. So I've only got to be a little bit out with my settings and I can easily clip the bottom of the beam or the top of the beam. As I found out in the previous session, the beam was somehow clipping the bottom here and some of the power was being lost because it was never getting through. Okay, that's a detailed look at the head itself, and it's quite important that you understand that. But what we're going to do is let's assume for a minute that the head is good enough, which it probably is, to allow me to set to its center point, which is here. The main reason I'm just showing you this drawing here is the fact that the bore is 17.2 and the difference between the beam center line and the true center line of that bore is 1.1mm. Okay, now this is probably the most important drawing with the least amount of information on it. Okay, so now we're on a completely different plane. Instead of looking from above, we are now looking in from the side of the machine. And the same rules apply when we look in this way as they do when we looked in from above. And that is, this beam must run parallel to the bearing rails. Now the bearing rail for Y is more or less fixed to the floor of the Lightblade, and the X bearing rail runs across the gantry that runs across the machine. So the gantry is set parallel to the floor, the bearing rail is set parallel to the floor, this bearing rail is parallel to the floor, and therefore the actual laser beam must be parallel to the floor as well. If it isn't, it ain't going to work. So, how do we achieve that? Well, we have got a fixed head. The head might be very slightly out, but if it is very slightly out position-wise, there's this little plate on the top here which allows us to direct the beam downwards and correct for slight, very slight manufacturing errors on the head itself. But in essence, what we've got to do is make sure that the laser is outputting its beam parallel to these rails. And it's as simple as that. So we cannot have this tube sitting like this. Or can we? Well, let's have a look at that. Because this is the most critical part of understanding about a laser beam's path. People ignore this axis. They concentrate on the plan view, which is actually easy. This is the bit that's going to screw you. Trust me. Okay, so very crudely, we've got our straight laser beam that's coming out of the laser and into the head. The laser tube itself is a very long tube, and the fact that it relies on this surface here, there is a part reflecting mirror, and right at the other end of the tube there is another reflecting mirror. Now those surfaces are absolutely parallel and normal to each other, so that the light can pass backwards and forwards between them. Now that's a mechanical fact. So that beam has to come out of there in a straight line. That beam can't come out of here at an angle. It's coaxial with the basic construction of the laser itself. Now even if this tube is very slightly eccentric, because the tube is so long, you can still probably assume that the external glass work will still give you a very good representation of the axis of the beam itself. So let's assume that we set the laser tube itself parallel to the floor. That's a good starting point, because everything on this machine is fixed to this ground point, this floor. Okay, so we've now got our laser beam travelling in a horizontal direction. But just in case we didn't do that, let's just do this for a minute. Let's make it slightly wrong. How do we deal with that? Well, we could raise this mirror here, because this mirror is adjustable. So we can raise that mirror up so that it catches the beam. But then we've got to make sure that it still runs parallel beyond there, which we can do, because we can swing the beam so that it sits parallel with this bearing rail. But then it means we've got to move this mirror up to catch that beam. So we can move that mirror up to catch that beam, but the head is not adjustable. So therefore the beam has got to run downhill to get to the head. And we can't allow that, because that means this part of the beam is now totally unable to sit parallel with the X-rail. So we may well have satisfied this condition here, but we can't satisfy it here. Now on my blue machine I don't have to worry about that, because I have made a bracket which allows me to move my head into line and catch the beam. This machine has got a fixed head and I don't have that option. So we've got to deal with it in a completely different way. That's why I'm saying this threw me, because I don't have the flexibility on this machine to play with. So everything has got to work from the centre line of the head. Which brings us back to this first picture here. That's what we're trying to achieve. Parallel to the bearings and straight into the centre line of the head. As I said, it's very, very simple to see on a piece of paper. How do we do it in practice? My background in design and production engineering says, spend the time and make it simple. Don't struggle. So what I've done, having spent the time and measured the machine up very carefully to establish what the problems are, I've also checked and found out why my beam is not correct. By using a very laborious iteration method, my axes did not pass through completely flat. And at this point, I was only 1.3 millimeters high. So, yeah, I got there. but it was a bit of a struggle, and I wouldn't want anybody else to go through that same pain. So I'm looking to try and make it a lot simpler and a lot easier by design. It would be a lot easier by design if the head was adjustable in 2 planes. It's not at the moment. And I say at the moment because if my first attempt at setting this machine doesn't come out too good, and you're going to witness that, you're going to see me go down in a blaze of glory or be a hero. Yet to be decided. But I always know that there's a backup plan. As I mentioned to you yesterday, I'm a bit of a wrecker. I'm very happy to take this head apart here and I'll make this adjustable. That way I can catch the beam just as I can on my other machine, and all of a sudden beam setting becomes a doddle. But I'm going to persevere with this machine because not everybody has the ability to go in and modify this head. So I'll stay with it as it is and see if we can generate a jig that people can emulate. Maybe they can't copy it directly because it depends on the layout of the various bits of the machine, but the principle you probably can copy, or you can modify the jig that I'm going to manufacture. I mean, despite the approximate setup that I used for beam alignment, it's cutting reasonably well. Here we've got the various pieces to our 3D jigsaw puzzle. Hopefully this will make the setting up of the beam and mirrors on this new Lightblade machine an absolute dream. And when I say dream, I mean maybe as little as 10 or 15 minutes. Who knows? But let's make a start. We've got a base plate. And on the base plate, we're going to put this piece, which sadly is not quite a match for the other pieces, but hey, the material was free, so we had to use the material that would fit the job. So I think the first thing that we'll do, and we'll just run some glue. I always like to work on kitchen roll because if there's stuff that goes through, then it let's just hold it upright and solid. Okay, well that's the basic frame, the base frame done. While that's just hardening off a little bit, let's just do this one. Now I could really do with keep making sure that this stays, although there's nothing, it doesn't fix to anything I don't think, no, so, but I will try and keep it upright. I'll use that once I've put my glue in. We'll pop this on next. We'll turn that upside down there so that we can just run the glue along the edges there. We'll pop the brackets on first, and then this piece. I'll just glue down these edges here. And we'll do the same thing on this end. We'll put our brackets on. And there is our finished jig. Now as I'm going to take the machine to pieces, I thought I may as well put a case extension on, because I could do with a bit more space between the lacer head and the first mirror. So I've got 3 pieces of 10mm thick acrylic there, which I didn't really have the right size pieces. So what I've done, I've just made myself a little jigsaw piece to make the frames up. So I've put 3 frames on there at 10mm, and that will give me a 30mm extension, which will be plenty enough. And there we go, there's our little 30mm extension. I've already started to do some destruction, but let's just explain what we're trying to do. What we've got here, we've got 2 mirror reference points. Now these mirrors are set the correct height from the base to match the centre line of this mirror here. Not the centre line of the hole, but the calculated centre line of the mirror itself. And these two holes represent the front edge of these two holes have to be roughly where the mirror faces are, and they will tell us the correct position in space, 45 degrees each, and the correct height. So we shall hopefully have 3 mirrors, which are 1, 2, 3 mirrors, all fixed, and they will be fixed at 45 degrees so that we know that they're in the right positions to start with. And then all we've got to do is hopefully tweak the mirrors, mainly in the XY direction, because we can't play with the Z. So we'll offer this up and you'll see what we're trying to achieve. Well, okay, we've now arrived at the moment of truth. We're going to start wrecking the machine and now undoing all the good work I did. There we go, 1 mirror removed. The thing is, when I look at this, there's a lot of adjustment on there, but there is no adjustment. It's right at the top of the stroke already. Well, we've removed the mirror, and I don't think we could have made it any more floppy than that. So we need to remove the Y-axis cable. We slide our jig in to start with, and then we hook it over the end of the gantry here. Just move it forward so that it slips over the socket that's in there, the Y drive socket. Now we've got a certain amount of movement in Y. Not much, but a little bit. Hopefully that's going to be enough to allow us to make sure we line all the mirrors up. Okay, now it's very important that the first thing that we do to both these mirrors, this one and this one, is to set the gap behind the mirror plate so that it's exactly 1 millimetre. And we're doing that with a hacksaw blade, and that's a millimetre, it just happens to be a millimetre. So we undo the screw until it grips the hacksaw blade. You can feel because the screw goes loose, and then just take the slightest amount of tension back on the screw and the hacksaw blade comes out. Okay, so we do that for all 6 positions on these mirrors. I've already loosened the screws on the base plate here so that I can slide it around a bit like this. Okay, because what I want to do is to slide it around in a minute. But before we do any movement of things now, we've got everything loose, everything's upset. We've got to set the beam to a known position. And the beam itself should push against its end stop. And that's the known position where I measured everything from when I designed the jig. So we push that against the end stop. The beam no longer moves, and because that's our reference that we're going to work from now. And the first thing we're going to try and do is to get this set nicely so that it sits snugly against that plate. As you can see at the moment, this mirror plate does not line up with this perspex plate. So it's set approximately to the right height now, and it's not too bad for position. So I'll just tighten up the screws on the bottom there. I think as you can see there, that's a pretty good match, those holes. And now we'll repeat the same exercise on the back here. Look, we've got this thing all nice and floppy. Let me just put my key. I need to do 2 things. First of all, I need to put that in approximately the right position and just put a little bit of tension on these screws. Just a little bit. Because you can see the brackets in the background are all floppy. So what I've got to do, I've got to push this against the plate now in approximately the right position. Let's just see if we can get it into approximately the right position and tighten up the screws. I've only got 1 screw that I can tighten up on both of the brackets. So there's 2 brackets and 4 screws, and I can only tighten up 2 of the 4 screws, 1 on each bracket. Now we'll tighten it up this way and see how much it moves. Now you're slightly out of line, so you're seeing a little bit of perspective there, but from dead on it looks pretty well aligned up. So I can take that jig out now. We've removed the jig, and I'll just now tighten up all the screws to make sure that nothing is going to move. And technically what we've now done, we've set this mirror and that mirror at 45 degrees to each other. They're the same height, and they're also the same height as the mirror down at the other end there. So we should have technically a nice straight line beam that runs through all the centre line of these mirrors. We're going to push the beam forward again. We're going to lock it up, because now we've got one more thing to do. Okay, now here we are at the back of the machine. I've got two pieces of kit that I'm going to be using now. This piece here, what it's designed to do is to take the laser tube. So it's designed to set the laser beam, which sits in here, the correct height from the base, from the floor, and also the correct position from the beam, the correct centre from the beam. And as you can see, they're loose. They're not in the right position at the moment, so I'll just lay that in there. This one, you'll see the reason why we've got this big notch in here now, and that's because we've got this water tube underneath here. I'm also loosening the fixings for the laser tube itself. Okay, I think you'll see that that's rather loose. Right, so that one's loose as well. We'll loosen this one off, and there are some screw adjusters on the top here. We're going to let those down, or we're going to wind them up so that the beam can sag and drop down onto the V-block. We'll do the same with this one. We'll wind the adjusting screw up, the collar, and then we'll put this onto its V-block, and we'll push it back against, make sure that it's sitting back. Yeah, we're pushing it back. There we go. Push it down and back. And now I'll tighten up these screws on this one. And again, if I just lift that up and let it fall down into the bracket, there we go. Now I'll just lock that up there like that, and I'll tighten up two diagonally opposite screws. Now we need our target, and this is the moment of truth. Now, before I start, I must remember to put the Y-axis plug on. I'll set my beam power to 15%, and we'll try a pulse. And what did we get? Surprise, surprise. Wow! Look at that! We're just a smidge off centre. And how do we get it back onto centre? To be honest, I think it would be very easy to just set that back another millimetre. And how I'm going to do that, I'm going to cheat. I'm going to stick a piece of masking tape across the back of that bracket, like that, and a piece of masking tape across the other bracket, and we're about just a millimetre off centre. So what I'm now going to do is to just gently slacken off these screws and tap it a millimetre across. Right, I've just slipped the laser beam across half a millimetre or a millimetre. That's looking pretty damn good. I just put a couple of pieces of masking tape on the back of the bracket here, and I slipped the bracket forward to give myself a 1 millimetre gap on here. So it's quite important that we put the mirrors back in before we have an interesting accident. Well, there's our target at the far end of the stroke. Just marginally off centre. And now we'll check it close in. I think that might be good, because there's a really strange characteristic coming into the beam. If we look, the beam is not even. Let's just do that test first. See, that's pretty central, height-wise, and slightly to the right. So we'll just check it at the other end of the stroke. You see, and that looks absolutely spot on. I mean, it's not spot on centre. Perfection that way, which is what we need. That's the most crucial direction, the up and down direction. We've got a little bit more latitude left and right. So, I'm pretty damn smug about that. Now I suppose there's one final check that we ought to carry out. Well, the good news is we've got a perfect set of incorrect marks. And by that I mean, I think you can see that they're all sitting down at around about 6 o'clock. And there's our final set of results. Not bad. They're all comfortably inside the target. They're nice round holes. There's nothing clipped there at all, so we've got a full beam that's passing through the nozzle. Well, there's the end result of our endeavours. I hope that you've learnt something from this exercise. I entered it with actually a great deal of confidence, because once I understood the principles behind setting this machine, I felt very confident that it would all work out well in the end. And to be honest, it has. It took about half an hour maybe to mechanically set the machine, and then it took about another half an hour to physically tweak the machine just through the mirrors to get it into a very good shape. And I hope that you won't have any fear in the future if you need to do the same thing yourself. Obviously, if this is the Thinklaser machine that you're worried about and you can see that you've got a problem, I suspect that you'll call in the service engineer. But maybe you'll be brave enough to have a go on your own. Good luck to you, and we shall see you in the next session.